My name is Chris Maka. I'm one of the owners of the store. I wanted to thank all of y'all for coming to our workshop presentation today. We're going to be doing a presentation on transistors. Again, we have a small business here. We really appreciate all of your help and support with helping keep our small business going, and all of your referrals are really appreciated. I'm going to turn it over today to Dr. Mike Condron, who's going to give a presentation on transistors.
So my name is Mike Condron, and a little quick background about me. Chris said doctor. I'm a medical doctor, but I spent a fair bit of time in graduate school studying physics and doing experimental physics on superconducting electronics. So I have some background in this, and I worked as an engineer for a couple of years during that transition period. So today I'm going to talk briefly about transistors, and I'm going to start off so this is the outline of the talk. Some basic electronics, a little bit about the history of transistors. There's a really useful model because it's very abstract what a transistor is doing, and understanding why it's doing it really doesn't help you understand how to use it. But there's a very nice model from a book called The Art of Electronics by Horowitz and Hill that I highly recommend, called Transistor Man, and we'll get to him. And that'll help really, if you only remember one thing conceptually about the way a transistor works, that will help you probably more than anything else. Then we'll do some simple circuits, a transistor switch, an emitter follower, small amplifier. I'll show you about something called the Darlington configuration, and then, if we have time, we'll get to a couple of other topics really briefly. So, some basic electronics. Most of us have heard of voltage. Voltage is the force that pushes current through wires, and current is the amount of electricity that's flowing. So voltage is like a pressure. If you think of water going through a pipe, voltage is like a pressure, and then current is the amount of water. And then the pipe has some resistance to the flow of water. So like a narrow pipe, it's hard to push water through it. A larger pipe, it's easier to push water through it. And that concept in electronics is resistance. And the parts that make resistance are called resistors. And there's this relationship here, Ohm's law, which says that the voltage on a circuit is equal to the current times the resistance, and you can rewrite that a few different ways. You can write it, probably the easiest way to understand is this one. The current is the voltage divided by the resistance. So you got 5 volts, 5 ohms, you will get 1 amp. Oh, the units. So current is measured in amps, named after a physicist named Ampere. Voltage is measured in volts, which is after an Italian guy named Volta. Resistance is measured in ohms, and I think he's German. These are the schematic symbols for it. For a resistor here, this is just a fixed resistor. This one is variable, and that's a fixed resistor with a thing you can slide around to get partial resistances between the two wires. That's the symbol for a battery. I'm going to be powering everything off with 9-volt batteries here today. Really briefly about capacitors and inductors, because these are a little bit more abstract. Capacitors basically are parts that store energy in an electric field, and they will generate a current if you try to change the voltage on them. They want to keep the voltage on them the same, and if you try to change that, they'll emit or accept current to keep the voltage constant. Sort of the flip side of that is an inductor, which stores energy in a magnetic field rather than an electric field. And inductors like to keep the current flowing through them the same, and they'll make a voltage if you try to change how much current is flowing through them. We'll talk about capacitors briefly. We'll use them in some of these circuits. I'm not going to do anything with inductors except the inductor that's in the speaker here. Okay, so to understand transistors, I think first you really have to understand diodes. And there are 2 diodes which I'm not going to talk about. And then there are semiconductor diodes, which are what I am going to talk about here. They're made out of either germanium or silicon. These days, it's extremely rare to use a germanium diode. They're almost all silicon. And they're formed by a junction of what's called a p-type and an n-type. And the way that that's formed has to do with some chemical impurities they add to the pure silicon. And it just affects the way that electricity can flow through them. Current can only flow that way. It's the opposite of how electrons flow, but what we call current, by convention, flows that way, from a P thing to an N thing. And if you try to make current flow the other way by putting a plus voltage here and a minus voltage there, no current will flow. So it's a teeny little bit. But the main way that diodes work is, once they get up to a certain voltage, a lot of current will start flowing through it. If you reverse it, no current will flow. We're all familiar with diodes. You may not realize it, but that's the D in LED. It's light-emitting diode. The light output depends on how much current there is. I didn't cover this part. There's a small drop in voltage, okay? So if you say the cathode over there is at 0 volts and you put 1 volt here, well, no, you can't do that. It'll come up to 0.7 volts and it'll stay there. No matter how, with other parts of the circuit, you try to raise the voltage up, the diode won't do that. It'll always have 0.7 volts across it. It's a little more complicated than that, but that's the essence of it. And I just wanted to put this point here that LEDs have slightly larger voltage drops. And we'll see that all this in a second with a practical demonstration. Yeah, originally LEDs were all red or infrared, but now they're available, as you know, in all colors, in white and ultraviolet and other stuff. So here's a graph about how a diode works. This horizontal axis is the voltage across it, and the vertical axis is the current that's flowing through it. So if you start off at 0 volts, of course, there's 0 current. And I wish I had something to point with. As you increase the voltage, you can see the current stays almost 0, and it starts to go up. And once you get to that forward voltage drop that I was talking about, which is 0.7 volts for silicon, all of a sudden a whole bunch of current starts to flow. And it goes up extremely fast. You can still increase the voltage a little bit, but basically you can think of it as it gets up to 0.7 volts, and then it lets so much current flow that you can't raise the voltage above that. It's a little bit different from that, but that's reasonable to understand it. Over here is negative voltage. If you reverse the voltage on a diode, a tiny little bit of current will flow, and this is just even magnified too much, just so you can see it. It's billionths of an amp typically. And it'll stay that way until you get down to this unfortunate point called the breakdown voltage, and it's well named. At this point, the diode can't hold back the pressure from the voltage that's being applied, and current will start to flow through it very, very fast, and typically when that happens, it'll overheat and slow. So you don't want to do that. Typical breakdown voltages for diodes, not LEDs, but normal diodes that are used in circuits, it's like minus 100 volts. So, yeah.
So are diodes rated based on their breakdown voltage then?
That's one of the specifications, also on how much current they can handle and how long they can handle it. So I'll show this in a second right here. So this is a data sheet from a diode, or this is a copy of a diode data sheet. I don't know if you can see it real well. The top yellow in here is forward voltage. So what that means is, I said 0.7, but this manufacturer is saying if you put 10 milliamps through it, they guarantee that the voltage will never be more than 1 volt. It will always be less than that. Okay. The breakdown voltage for this diode is 100 volts, and they give some parameters for how that was measured. And then there's this purple one here, the forward continuous current. For this diode, you must, if you want to put current through it in a continuous manner, not as a pulse, you can only do it up to 300 milliamps. And that has to do with how hot the diode's getting and how fast the package can dissipate the heat. You can see here, if you want to pulse it for 1 microsecond, you can put up to 2 amps through it. So it's just a matter of how fast you can dissipate the heat that current is representing.
Are some diodes way faster than
Oh
others?
yeah.
Okay, so you can specify a very, very fast rise.
Oh, you mean how quickly it rises? That is more or less pretty constant from one diode to another. It's sort of dictated by the physics of the part. There may be some that are a little bit more turning on faster than others with a slightly different shape, but it's always going to be pretty close to the same thing. Okay, so here is a little circuit showing how to turn on an LED. And here is the grounded output. Here's the, okay. So what I have over here, this gray box, oh, these are transistors, by the way, here. They're typical package for them. I'm going to be using this box a lot. It's a signal generator, and I've got it set up right now to make a sine wave, but what I want is to make it make DC. And, okay, that should do it. I'm going to move that out of the way and put the circuit in view here. We're going to be working with this yellow LED here. And I have my 9-volt battery. I'm going to hook it up to the power lines of this. There. And we don't actually need the power, the 9-volt battery power for this demonstration. It's going to be coming from the signal source. There's a lot of different kinds of breadboards. This is a fairly good
I'm
one.
not normally here on
It's
Saturday.
difficult to shove wires into it though sometimes. Okay, so right now, there's no voltage coming out of here. It's 0 volts. The diode's off. Okay, no. Now, as I increase the voltage, right now it's at 0.1, 0.2, 0.3, 4, 5, 6, 7. This better work. Okay, there we go. Okay, great. So right now we are at about 2.3 volts. That's 2.0 volts. Now, that is the voltage here. It says 9 volts here, but it's the signal source. So it's a variable voltage. That's not the voltage on the LED. That's the voltage across here. So there's current flowing through the resistor, which will lower the voltage. And then the LED will keep that 0.7 volts there. So this will be higher, that's going to be at 0.7, and then there's voltage across the resistor. And you can probe that. What you can see is I increase the current, it gets brighter and brighter and brighter. Okay. And actually, let's just move on to the next thing. That's pretty clear to everybody, right? You increase the voltage, the LED turns on, there's more current. Okay. Okay, so what I have there, it's a 3.5 volt with an offset. So now it's a 3.5 volt triangle wave, which needs to get bigger. There we go. Okay, and I will hook up the oscilloscope to it so we can see what that looks like. There. So that's the shape of the wave that the source is applying across the resistor plus the diode. Okay, it's going positive 2.5 or 2.6 volts, and it's going negative 2.5 volts. Okay, let's turn that up a little bit, maybe up to like 6. So now it's going positive 3, negative 3. You can see this is the positive 3, there's the negative 3. All right, and the diode's flashing on and off. The frequency is 10. Let me change it down to something a little slower. Oops. 0. There's 1. So that's 1 cycle per second. Now it's not, you can see when it triggers again there, you can see the voltage is totally symmetrical, right? It's half the triangle is above and half the triangle is below. But if you look really carefully, the light's not on 50% of the time, right? The reason for that is that you have to get this voltage across the diode up above 0.7 before it turns on. So it's really like the diode's idea of 0 is kind of like here. And so it's spending less time on. It has to have at least 0.7 volts across it to turn on. Okay?
So do you consider that like an alternating current, what you're doing?
Yes,
Okay.
definitely, yes.
But it's a direct current just pulsed, right?
Well, it gets into what you mean exactly. I mean, a direct current technically is like what's coming out of the battery, just a constant with no time change at all.
Right.
Pretty much anything other than that, you know, sort of talk about alternating, but some people use the term to mean a voltage that's always positive, rather than one that goes positive and negative, and then it's sort of like how do you want to use the words? Okay. Yeah. But
LEDs, right?
yes, that's 2 diodes back to back. So one's on, the other's off, and there's still that 0.7 volt issue, so they won't be on at the same time unless they do some tricks to get around that.
So that would be going high in one direction, the other with the cycle or whatever.
Exactly. Okay, and then I have one question here at the end. Where is the power to light the LED coming from? It's not going to just turn on all by itself, right? You need some electricity. Where's that coming from? Here. From the signal generator, right. That idea is kind of important. Oh, you know what? There's something else I wanted to show you here real quick. There, see that? On the blue trace? That's what I'm touching right here. Where's that coming from? Is that my heartbeat? My brain waves? No. That's noise in the air around us from power lines. And our bodies can pick that up. And this probe doesn't draw hardly any current at all. Now if I try that with the speaker, that doesn't work, right? I can't power a speaker off of that signal that we just saw. That idea is going to be really important. This scope probe draws almost 0 current. And the term for that is it has a very high impedance. It doesn't take any current out of the source that's trying to provide it. The speaker has a very low impedance. And so when I put that voltage in, it's a lot of volts. I think this is the blue channel, I think is on 10 volts per channel, or 10 volts per division. So it's like 10 volts across just from picking up stuff in the air. But the impedance of that inside of me is so high, as soon as you put a speaker on it, that voltage drops to 0. And this concept is going to keep coming up as we go through this.
So let's say most speakers are 8 ohms. What would a comparable impedance be?
This scope probe has an impedance of 1,000,000 ohms. And actually it's configured in a way that it looks like it's 10 million.
You don't need to. Thank you.
So there's a big difference. Yeah. Even 100,000 ohms would drop that signal from my fingers to almost 0. Alright, so I think we've covered all the LED stuff. Now we'll start talking about the transistor. A little bit of history. It was first developed in 1947 by a group of people in Bell Labs. They were not trying to invent it, they just kind of found it, doing something else. Bell Labs, by the way, was a division of AT&T. Almost everything that you know of that was invented in the 20th century, it came out of Bell Labs, or was derivative of something that was invented in Bell Labs, going back to 50 years or more. It was a really amazing place, so it still is. So these three guys won the Nobel Prize for doing that in 1956. John Bardeen is kind of a personal hero of mine. When people think of famous physicists, who do you think of? Einstein, Feynman. Most people probably can't name any other ones. Well, now John Bardeen, you know. Einstein was a pretty smart guy, and he won a Nobel Prize in physics, and so did Feynman. But guess how many Nobel Prizes each one of those guys won? One. John Bardeen is the only guy in history to win 2 Nobel Prizes in physics. And these are given during your lifetime, so it's not like you can get it after you die. So twice in his lifetime he did something so big that he got a Nobel Prize. This was one. The other one was what I've studied in graduate school, which is the theory of superconductors. Brattain, I don't know too much about him. Shockley, he was a pretty smart guy too, but he went off the deep end later in his life, and if you know anything about the history of William Shockley, he kind of lost his mind and started doing some pretty writing about things. So what they developed was what's called a point contact transistor. What we use today almost always is what's called the bipolar junction transistor. There's another kind called the field effect transistor, which I might cover a little teeny bit at the end. It works kind of like 2 diodes back to back, but not really. There's a complicated picture up there that shows a hint of the physics of what's going on in there. You can see that on the top, there's that picture of the diode. And then underneath it, there's sort of a conceptual model of a transistor. There's an N and a P, just like in the diode, but then the transistor has another N. Now normally, if you remember about the diode, you can't make the current go backwards from the N side to the P side. The transistor's got 2 N's and a P in the middle, so you would think that no matter what you do, you couldn't get any current through it at all. And that's almost right. But there's a little bit of magic that happens when you start putting current into the base. If you put current into the base enough to turn on, I'll talk about base emitter and collector in a second, but that's the names of the leads on the transistor. If you put enough current through the base to turn on the base emitter junction, all of a sudden current will flow backwards through the collector. And that's the whole essence of what a transistor does. It looks symmetrical here. I put this picture in here because a lot of times people wonder, well, gee whiz, NPN, why can't I just reverse the collector and the emitter and have it work either way I want? The reason is they're manufactured like that. They're not manufactured like that. So they're not really symmetrical. The collector's designed to collect stuff and the emitter's designed to emit stuff. So they're not really interchangeable. It'll kind of work, but not quite. Yes? You have a question?
Did they ever make a transistor that was symmetrical or close to symmetrical like that?
Yes, they definitely can. But there are reasons why not to do that. It affects the way the thing performs at high speed and small voltages and things like that. Okay, so there's 2 kinds. This is an NPN transistor. You could also make a PNP if you just swap the P and the N, and they have different properties and they're both useful. We'll get to that. So here's a way that you can think of a transistor from the way an ohm meter would see one, okay? It looks like a diode from the base to the emitter and another diode from the base to the collector. That's an NPN. PNP is the other way around. This is not how they work, though. If you try to take 2 diodes and do that, you won't get a transistor because that magic, when the base and the collector and emitter are very close together, the base is very, 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 very thin. That magic doesn't happen through just a wire when you connect them. Okay, so now we'll start talking about the model for how to think of how to use one of these things in a circuit. This is probably the most important rule right here. The current through the base controls the current through the collector. This is a mathematical relationship. That I means current, C obviously is collector. For some reason in transistor work, they use the symbol beta, the Greek letter, to refer to this ratio. So it's like the collector current is proportional to the base current. That ratio is just called beta. Sometimes you'll see it written as HFE. Usually people say beta. Beta is typically around 100. Some transistors it's 50. A lot of the transistors I have here I measured and it's like 400 or 500. It depends on the design of the transistor and what the intended use is. So yeah, this is super important. It looks like it's in bold and highlighted, right? Yes?
Is the HFE the amplification factor? Current?
Not quite. To make an amplifier, we'll get to an amplifier, but it's sort of amplifying current. So you put a little bit of current into the base and it can control a huge amount of current through the collector. And we'll start to see examples of that coming up. Now I mentioned Transistor Man. This, like I said, is a very important and very useful model for how to understand transistors. What do we see here? First thing we see is there's a guy standing here with his hand on a variable resistor, right? And he's looking at a current meter in the base, and he's looking at a current meter on the collector. The collector current is bigger, and there's this diode here. That is the base emitter diode. This is the diode that has to be turned on in order to get any current flowing through the base at all. Once that happens, Transistor Man, he's got one thought on his mind. You see that there? The collector current is HFE times the base current. That is his job. That is his mission in life. How can he achieve that? He does not have any batteries, doesn't have any current sources. All he has is that variable resistor there. And he's going to change that resistor to make that happen, however he can. Another thing to notice, this resistor can go up to be a wire. It can go all the way up and be zero. It's not in reality zero, but it's darn close. The other thing is, it can go off the end, so that no current is flowing if the transistor is off. If there's no base current, there's no collector current. All right? And I think, oh yeah, see, I highlighted these and then I talked without even going through the highlights. But here's, okay. The other thing to notice here is he's got something in his hand. And that is his contract, his employment contract, his deal with you for when he's going to do his job and under what conditions. And here are those conditions. The collector has to be more positive than the emitter. So a transistor can only conduct current one way, through from the collector. This is for an NPN transistor. The collector has to be more positive than the emitter. And I'll show a picture of this in a minute. The base emitter junction has to be conducting. That was that little diode on the side there that he's looking at the current flowing through it. That diode must be turned on. And the base collector junction has to be reversed. So what that means is the base has to be in between the collector and emitter voltage if you want the transistor to be working. There are maximum ratings for the collector current, the base current, and the collector emitter voltage. Just like with a diode, you can only push so much current through it. With a transistor, there's the same kinds of rules. They can only take so much power going through them. If you violate those rules, you will lose your transistor. I mean, he doesn't just stop doing his job. It's like he turns into a puff of smoke. It's literally. So, when rules 1 through 3 are obeyed, then Transistor Man starts doing his thing. And this was all formatted nicely when I laid it out at home, and now it's getting chopped off. Remember also, he has no current sources and no batteries. Transistors don't make power, they control power. So, how do we apply these rules? A typical NPN circuit will be arranged like this. That's an NPN transistor fake picture. I really wish I had something to plug with.
What do you need?
A pointer? Anything, like a pencil or a pen. Just a little bit, kind of tall, but I can't quite make it out there. Oh, thank you. That's the pin that was lying right there. Okay, thanks. Yeah, I brought it then. So, all right, so the emitter typically on an NPN circuit is connected to ground, or something else that's connected to ground. The base has to be at a higher voltage than the emitter. The collector typically is going to a power source or something that's connected to a power source. And then we're going to show different configurations of this in a minute. Under those conditions, then the output, whatever it's derived as, is going to be related to the collector current. That's going to be controlled by the base current. That's what the transistor is useful for. It lets you take a small amount of current and control a large amount. Equivalently, it takes a small amount of power to control a large amount of power. Okay.
Does any of that
yeah.
base current leak into the collector emitter circuit?
It goes into the emitter.
Okay.
Because this, the base voltage has to be higher than the emitter, so the current's going to go that way.
Okay,
See
we'll
the
come
diode
in,
there?
yeah.
Yeah. Now, again, this model is not the way a transistor actually is. I just had to put something there to have something to kind of have this make sense. The base collector junction is reverse biased. That means that this voltage here has to be less than that voltage there. If that's violated, if you bring this voltage up above the collector voltage, what happens? This diode turns on. And remember what happens when a diode turns on? You get huge amounts of current, and that will also smoke the transistor, so you don't want to do that.
And so, you fill up that
Okay, now getting into some applications.
So anyway.
There's two broad categories of applications for transistors. One is a switch, the other is an amplifier. It's the same transistors, sort of. Some are optimized for different applications. A switch works like this. If the base voltage is large enough to turn on the transistor, then collector current flows. If the base voltage is lower than that, then no collector current flows. And this is how they use transistors to make logic gates, too. They have fancier transistors with multiple emitters and things like that. It's the same basic concept.
How did you make those transistors?
I'm sorry?
Could you make one of those transistors with multiple emitters by putting two transistors in disconnecting the base and collector to each other?
No. These things need to be made on the actual transistor material itself. You can't do it with wires. It won't work.
Now, couldn't we have made logic gates with, I guess, vacuum tubes or relays?
Yeah. And you don't need the multiple emitter transistors to make logic gates. It's just that's the way that most of the modern parts are done.
So why did logic gates all of a sudden kind of explode after transistors and that became a thing?
Oh.
Were they doing it before transistors?
They're way smaller. I don't know if you noticed.
Yeah, they're smaller.
They're obviously a lot smaller than vacuum tubes. They're also much faster, and they're more efficient, and they don't need a heater. So a vacuum tube computer maybe that could do some simple things might be as big as this entire bench here, and that same thing with transistors might just be like this, and use probably 1/100th as much power, and generate 1,000th as much heat. So for an amplifier, the way that works is you turn the transistor on in between, all the way on and all the way off, and keep it there, sort of in the middle. And then you apply a small voltage on top of that, it's enough to turn it on. And the collector current will be much bigger, and there's a way to convert the current to a voltage, I'll show you that in a minute, and then you get a voltage gain, and that's what we think of as an amplifier. So those are the two basic applications. Now, here's a switch. This is a very simple switch circuit. There's a transistor here, it's NPN, the emitter's connected to ground. Here's a battery, we'll use 9 volts. There's a resistor there, an LED here, so the LED needs some current through it to turn on. And then there's a voltage here and our ground thing. So when this ground goes up high enough, the current will start flowing through here. Eventually, and this voltage will start going up. Eventually, this transistor will turn on, and then the collector will turn on. The collector will start having current flowing through it. Okay, everybody with me so far? Okay. As we keep increasing this voltage, we'll keep increasing the current that's flowing through here. Eventually, it'll be enough to where the LED turns on. And what's neat about this, you could just say, well, why don't you just hook VN right to the LED, like we did with this little yellow LED here. The reason for that is that the current that's going to be flowing through here is much less than the current flowing through the LED. It's going to be that beta number, like 100 times less. And I took advantage of that fact when I built this little guy here. This is a circuit that I made to hook up to a little computer that I have that can turn on these LEDs from a digital output. You can see the transistors here and the resistors that are needed to make that happen. And the reason I did this is because the outputs that I wanted to use for it can only provide a very small amount of current, not enough to turn them on. So I needed something else in between to provide that boost, and that's what the transistors do. Let's see, did we talk about all of this? Yes, we talked about all of this. One thing I haven't mentioned is the collector-emitter voltage. There is a little bit of a difference between the collector and the emitter. When the transistor's all the way on for a silicon transistor, the voltage between the collector and the emitter is like 0.2 volts. It's very small, so it's kind of almost like a wire. Yes?
So in this circuit, even though there's a power source in the outer loop, power still can't flow until that transistor opens? Is that
Yeah,
correct?
there's a teeny bit, but basically this transistor looks like an open when there's no base current flowing.
Anyway, I'm gonna go over here.
What's the resistor for? The resistor to the base.
You can, the resistor to the base. That is to stop too much current from flowing through the base out the emitter once the transistor turns on. Remember that diode curve with the really sharp rise?
Is that the control of breakdown?
Well, breakdown is when you're putting it backwards. So yeah, if I took this, here's 0 volts, if I put this at like minus 100 volts, that would be breakdown. This is just too much forward current. So if I bring this thing up to like, 1 volt without that resistor there, that diode that is in the base emitter junction, that diode will turn on and amps will start flowing until there's smoke. Yeah, so that's what the resistor is for, is to limit or control how much base current is flowing for a certain amount of voltage there. Yes?
Also, if you were to just connect without that resistor, the transistor would also overheat.
Yes, unless you had a way of controlling how much current is coming out of here.
Or you had a power transistor that could dissipate.
Right, you could do that too, yeah. And I wish I had
That
some
base
or something else up
emitter
here.
voltage is usually
That's-
the lowest.
Right. Oh. Right, okay, we'll show that. How do we calculate these values? In most books, you just kind of see R1, R2, and you're left to kind of figure out, well, what are they supposed to be? I won't go through this in great detail, but the idea is you pick how much current you want flowing through the LED when it's on. You know the forward voltage drop across the LED is 1.8 volts. I measured that. Okay. 9 volts here, 1.8 volts there. That gives you the voltage across the resistor. You can use Ohm's law. I know this is a lot of math, but there's no other way to go through this. And if you grind through all the numbers, you'll end up with a value for these numbers here of 1,747.5 ohms. Do we have any 1,747.5 ohms? No. So we'll just round it off to 1.2 thousand. Actually, I think that's from an earlier version of this I did. I think I'm using 1.8 in here now. And then for R2, you can run through the same thing. How much collector current is there? We can divide that by beta. You know the base emitter voltage drop. And you can run through the numbers again, and I got 8.2K. I believe that's what's in there, but like I said, I went through some revisions of this. And it would be a little different. Yeah, 8.2 and 1.2. All right, now let's try to get that working. That is the red one. And you can see there's the base resistor, and the one at the upper right is the resistor for the LED. And now what I want to do here is turn all this down. And I'm going to stick this one there. So, okay, we can still see this. I'm going to turn up the frequency just a bit. So this is easier to see. Maybe like a little bit faster. A little bit bigger. Okay.
Are those resistors the same value? Or do they just look like the same color in the picture?
One should be 8.2 and the other 1.2, and they probably just look, 8.2 is going to be gray, red, red, and 1.2 is going to be black, red, red, so they're black and gray.
Yeah.
Dark gray, light black. Yeah. So here's what's going on. When the voltage gets high enough, you can see the LED pulse, and it's not doing it through the whole cycle for the same reason the other one was also not doing it through the whole cycle, because the voltage is negative for part of the cycle. It's also not doing it half the cycle for the same reason. It has to overcome that 0.7 volt thing, only that now that's not the diode, it's the base emitter junction. It has to be bigger than 3.7. Now right now this is a 1.6 volt peak to peak square wave, or triangle wave. If I turn that up, what am I turning up? I'm turning up the frequency. I want to be turning up and maybe I should slow the frequency down so we can see this better. So now it's turning it on all the way. Now it's kind of going slow. It's not all of a sudden just snapping on like you'd see maybe with the relay or something like that. And that's because this is a slow input thing, and it's not, the transistor isn't an instantaneous switch. It makes a transition, a gradual transition from off to on. Okay? But we can compare. What happens if you do the other one? Just the LED. I mean, yeah, just the LED plus the diode. I mean, the LED plus the resistor. There. So now you can see the yellow LEDs kind of slowly turning on, slowly turning off. The red one is much, much faster turning on and off because of that, the way the transistor is amplifying the current. It quickly goes into saturation and looks like a wire. Yeah. Now if we applied a pulse to it, it would be even faster, but this gets the point across. Yes?
So if the transistor, if we're controlling the base current to control the collector current, so why would we use R1 as a current limiting resistor?
Well, if R1 wasn't here, then you start turning this on, you start raising this voltage, you turn on the base emitter, and then a little bit of current starts flowing through here, and the transistor turns on, and there's nothing limiting the amount of current that can flow here. This will just look like a short. Now at the beginning, if you're very precise and walk the voltage up teeny, 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 the voltage here, transistor man is doing his thing. He's saying, okay, there's, you know, a milliamp flowing here, I'm going to make 100 milliamps flow there. But eventually it gets to a point where this looks like almost like a wire. And the LED, the transistor may survive, but the LED won't. You'll be able to put so much current through the LED that it will get damaged. So this resistor just sort of controls how much, it's like the ratio between your battery voltage here and how much current you want flowing through the LED. And they can maybe handle up to 10 or 20 milliamps depending on the part. It varies a lot. And how much light they put out varies a lot too.
So if there is a current limiting resistor on the collector, so
yes.
So the resistor on the base is not critical at 8.2K, right?
I like to think of them not really so much as current limiting, but rather, I mean, everything is going to limit the current. The LED will limit the current by just evaporating if you put too much current through it. This isn't really limiting current. I know that term's used a lot, but a better way to think of it is it's controlling the relationship between this voltage and how much current you want here. So if you want 1 milliamp here, you'd use a certain value based on calculating the voltage drop and all of that. If you want 10 milliamps here, you'd use a smaller resistor. If you want a microamp, you'd use a bigger resistor. So that's really, it's controlling the ratio between this voltage and how much current you want going through the LED. You know, if this was 1 volt, you need a smaller resistor. If it's 100 volts, you need a bigger resistor. I know the term current limiting is used a lot, but it's a little bit more than that. It's the relationship between the voltage you've got and the current that you want flowing through the part. And the same thing is true here. You can make this smaller, and then a smaller voltage will turn on the transistor. You can make this bigger, and then it'll take a larger voltage to turn on the transistor because of the less current flowing with the larger resistor. Does that make sense? Okay. So yes, we've done that. In the interest of time, I'm not going to do some of those measurements, but I will ask this. This is a critical concept to get here. Where is the power? I asked this with the yellow LED, where the power for it was coming from. It's coming from the signal generator. Where is the power for the LED coming from now?
Battery, right?
It's coming from the battery, that's right. And that gets back to this idea that a small amount of current or power here can control a larger amount of power coming from a different source on the other side of the transistor.
So just, I'm sorry, I'm pretty novice to this stuff.
That's fine.
So one resistor is just controlling the enhanced the LED just so that it doesn't glow. Right?
Well, again, I like to think of it as deciding, I made the choice of that resistor based on how much current I want through the LED with a 9-volt battery.
Okay.
Yeah.
Like if you put like a 5-volt battery, it would be a totally different if you needed it all, right?
Like half.
Okay. But that, and the transistor itself is just acting almost like a resistor as well, because it's going from being a wire basically to being nothing also, right? So it's a variable amount of current. Is that
Yes.
correct?
Best go back to transistor man.
Okay.
The base current
He's
is there.
turning it closer to the wire as the...
Yeah.
Okay.
As the base current goes up, he's getting closer to the wire.
Okay.
Yeah. And it gets to a point where the transistor is in what's called saturation. You put as much base current through as you can get collector current going, and that's how you operate a switch. You push a lot of base current through, and then the collector current goes way up really fast, and the collector emitter voltage drops really fast. So it looks like very, very little resistance when that's happening. Any other questions about this? Okay. Yeah, we did that next. There's a really cool, this is digressing a little bit, there's a really cool website called circuitlab.com where you can draw circuits and run simulations with it. I don't want to get into how it works, but this is a simulation of this circuit here. This is the base voltage, the blue line, and that's the current through the LED, the orange line. See, it's really sharp, it goes up, it stays flat, and it comes back down. That's what we would like a switch to do. And again, that's the base current, and that's the collector current through the LED. And then this is showing the base voltage. Here's that 0.7 thing. It's always going to be there. When you try to turn on any PN junction, you're going to have that plateau of 0.7 volts. And if your voltage is less than that, there's no current flow. And then it goes negative because there's nothing stopping it from going negative, only going positive. And then this is again showing the collector current here. So this is how what a switch ought to look like, right? You get up to a certain threshold and wham, it turns on. You get down and bam, it turns off. That's a nice switch. Why not do this? Before we have the LED over here, what's wrong with putting it there? It'll work. I've done it, but it doesn't work so good. And there's a couple of reasons why. This goes back to that thing I had at the beginning earlier, which was in an NPN circuit, not always, but usually you want the emitter to go to ground, and then your stuff is in the collector circuit. And here's some reasons why. I mean, this will work, but if you do this, you need to have a higher voltage here, because now you've got to get that 0.7 here, plus now you've got this LED wanting its 0.7 across it. So you now need to get this up to 1.4 volts to turn the LED on. Furthermore, as you put more current through this thing, its voltage is going to rise up a little bit. So as you turn it on, it's fighting against you turning it on. And sometimes you want that, but in this kind of circuit you really don't. So this, it'll work, but it won't work as nicely. And here's a comparison using that simulation again. This is what we had right here with this red LED. You can see it turns on really good. This is the same input voltage, but now look at this. It's kind of got this weird over here, and it goes up slower, and it does this weird little bump there. That's because of that LED turning on and fighting against the base voltage that's trying to get the base current through it. And again, sometimes you want that, and we'll see an application for that in a minute, but not right now. However, what if we have something where we need the load to be connected to ground? Here we can put the LED connected to the plus side of the battery or the minus side of the battery, doesn't matter. But maybe in the real world there's something that's got one side of it bolted to a grounded wire, and you can't hook it up any other way. Here's our first application of a PNP transistor. We've been talking about all NPN transistors up to now. it works kind of the same way, but it's sort of reversed, okay? This idea is still there. You forward bias the emitter-base junction, but you do it by bringing the base to a lower voltage than the emitter, so that this diode conducts that way, okay? The current will flow out of the base, and current will still flow from the emitter to the collector once this transistor turns on. It's just all the polarities are backwards. And I've got a circuit for this. There we go. So here's a PNP transistor switch. So here we've got the emitter. The emitter is the one with the arrow on it. I didn't say that earlier. And by the way, you can remember which is which, NPN and PNP. Like in NPN, the arrow's not pointing in, right? NPN. And a PNP, I've heard different things, but just PN is good enough. Pointing in, some people say pointing in proudly. Think of it that way if you want to. So this is the emitter of the PNP transistor. It's hooked to the plus part of the battery, and then this will turn on when this voltage is low, right? If it's lower than the battery voltage minus 0.7, which for a 9-volt battery is 8.3. So when this goes below 8.3, this base emitter junction turns on, currents start flowing, and then Transistor Man does his thing. He makes the collector current 100 times, or beta times the base current, and then that'll turn the LED on here. And so it's the same as an NPN. You've got the emitter hooked up to the power source. The load, the thing you're trying to control, is on the collector side, and you have to turn on the base emitter junction. And almost everything is the same, except the polarities are the other way around.
Is that like one is an always on and one is like an always off? Is that,
it's more like one is on when the input is at a high voltage, and the other is on when the input's at a low voltage. Okay. And I've got a demo set up right here.
Do low voltage cutoff circuits work similarly to that? A transistor detects voltage drops below a certain point, and so then it cuts off power to whatever?
I don't know exactly what that circuit is. I'd have to see it in context. Okay, so now we have here the green LED. And that transistor there is a PNP transistor. And so the orange wire there is the input. You can see the resistor to the base. And I didn't talk about the wiring of the transistor parts. Maybe I'll get to that later. But the left one is the emitter, the middle one is the base, and the right one's the collector. And then there's the LED and the resistor to ground. And I need to change the voltages again to make this work. I experimented with this earlier this morning, and I found that 10 volts with a 5-volt offset right where I want to be to make a nice point here. There we are. And this is so that's the wave that's going into it. Now this time, the blue line is 0. That's the other channel, and it's got nothing hooked to it. So that's a nice reference for 0. And then the signal I'm applying to it is going up and down from 0 to 10 volts. And the LED is turning on when it goes down, below about 8.3 volts. Okay? So it's spending most of its time on, because 8.3 volts on the scope is right about there. And most of the time, it's below that. And that's very useful. In fact, that's how this thing is set up, because the parts that are driving this board to turn on the LEDs from the computer's port, it turns out that those outputs can have more current going into them than they can provide going out of them. So I set this thing up this way, so that when the voltage is low, the transistor turns on. And it's confusing because you think of putting a voltage high should turn it on, but it just doesn't work that way here. And now I have that last little fun item to try. And this is what took some tweaking this morning. Is to hook that same source, all three of these things, there. So now you can see well, they're all on at different times, right? One of the red one's on when the voltage is above a certain point, way down here. The green one is on when the voltage is below up there. So they're not on at the same time, right? And then the yellow one is just kind of turning on and off because he's always getting a positive voltage through the whole cycle, but it's not always enough to get past that 0.7 PN junction voltage. Okay, any questions about what we've got here so far? The PNP thing, the NPN thing, the switch, the PN junctions. All right, good. Now, I mentioned before that usually we want to have the load of a circuit in the collector part, the thing that's being controlled, and we want the emitter to be connected to ground, but I snuck in really fast, or something that's connected to ground. Okay. If we do this configuration here, now before I had the resistor there and an LED here, we were trying to control what's going on with the LED. That's our objective here, is to control the LED. When you put the LED here and the resistor there, that has some suboptimal properties that we saw. But if you put the resistor here, this is a whole different circuit. This is what's called a programmable current source. And I'll run through how this works. And you can put any load here that you want. It doesn't have to be an LED, just anything where you want to put a fixed amount of current or a controllable amount of current through it. So here's how it works. The emitter voltage is basically the base voltage, but it's minus that 0.7, okay? There's no resistor here in the base. What's limiting the base current and stopping the transistor from smoking is this, because the base current will flow out the LED. So yeah, the emitter voltage is the base voltage minus 0.7, or we can think of it as they're kind of almost the same thing. So the current flowing through the emitter is the emitter voltage divided by R1, that's Ohm's law, right? So the emitter voltage is just the input voltage minus 0.7 divided by R1. If beta, and I know I'm going through this really fast, I'm sorry, but there's no way to do it any differently. If beta is very large, then the collector current is almost equal to the emitter current. What that means is the base current is very small compared to the collector current. The emitter current is the base current plus the collector current. So if beta is really, really big, almost everything that's coming out the emitter is just what was going in the collector. Okay? So with that approximation, we get this. The collector current is just, forget about the 0.7 for a minute. The input voltage divided by R1. That's pretty cool. And it doesn't matter what this is. It's all, the transistor man will adjust things within his capabilities to keep the current there equal to beta times the current here. And so you could make this a wire, you could make it a resistor, you could make it an LED, and whatever voltage you put there, this current, this relationship right here, will dictate how much current is flowing through there. Let's see that. And I don't want to blow anything up here. Actually, I won't blow anything up. I'll just knock people's eyes out of their sockets with this LED here. So this is a white LED, which I think are pretty cool. When I was a kid, we didn't have even green LEDs. Now we've got white ones and everything. Let me turn these off because they're sucking a lot of power from my battery. Okay, so right now we're at 0.6 volts, and I'm sorry there's no way to have. Oh, there it is. That's still there. Okay, so right now we're at 0.6 volts, 0.7. Oh, and the resistor. I have a picture of this. Yeah. Oh, and the ammeter. See, I'm glad I went through all the stuff of putting their little notes to remind myself of what I'm doing, because I will forget in real time. You can see it. Probably works better if I turn it on. So this is a meter that shows how much current is flowing through it. And I've got this thing set up so that I can measure the current through the LED. And it looks like it's already turned on, but it's not. There's no current. This doesn't have a way to stand it up. Set it right here. Okay, cross your fingers. This thing should turn on at some point. And there should be current. Now, the reason for that is that's controlled by this. Yes, now let me switch it over to constant current. So right now it should be putting out 0.6 volts. The resistor that I put in there, 330 ohms, and I did that for a reason. It makes this particular part of the demo a little bit confusing, but it makes sense in a minute. So 0.6 volts. Let's turn it up to, whoops, like 1 volt. Okay, so 1 volt, there's the 0.7 across the diode, right? Go back. So there's 1 volt here. Oops. Yeah. No, there's 1 volt here. There's the 0.7 volts across here, so the emitter is 0.3. And that's why it's 330. Because that's subtracting that 0.7. Unfortunately, it's showing 8.7 milliamps, or 0.87, so the resistor might be a little off or something like that. And we're not quite at the diode's filter stage yet. But as I increase the voltage here, you see the LED gets brighter and brighter and brighter. And these things can get unbelievably bright and still do just fine. So now we're up to 8 milliamps through that LED. You can probably see it from all the way across the room, right here. Yeah. So now if I took that out and put something else in there, within reason, it would put the same amount of current. Right now it's putting 8.9 milliamps through, and that's going to stay the same. So that's what a programmable current source is for. And that's another thing that a transistor is really good for. And these are very useful things to have in circuits. Okay. Oh, what else do I have here? Yes.
So the Vin is a lower voltage battery voltage, right?
It doesn't have to be.
I mean,
Or
in this
no, wait.
case.
I would have to think about that. In this case, yes. But it,
So is there any current flowing into the Vin from the collector?
you mean here?
Yeah. is
Actually,
there
it was
current
higher.
flowing this way?
I can turn this up quite high. It doesn't matter. As long as this is reversed. So as long as the base voltage is less than the collector voltage, then it can be anything.
So if we replace the LED with a piece of wire, so it will still be the same current.
Yes.
So it is the, I guess, transistor. It is acting as a variable resistor according to the mode. Is that?
Something like that. It's acting more like a current source, which is a little bit of a hard concept. It's sort of like the current version of a battery. A battery, it's got 9 volts on it. You can take current out, and within certain limits, it's going to always be 9 volts. A current source is the flip side of that, current. It will force, say, 1 milliamp through itself, no matter what you connect to it. If you hook up a wire, it puts out a billionth of a volt, just enough to get through the resistance of the wire. If you hook up a large resistor, it'll go up to as high a voltage as it can make to keep that same current going. And that's what Transistor Man is doing in this circuit. He sees the base current, and then he makes the collector follow that current times beta.
I'm trying to think of some applications for like music.
Okay?
So I know that they use transistors a lot for like fuzz pedals.
They're used for all kinds of
So
stuff.
that's kind of like it's turning. If you were to replace, if you have like this triangle wave going in there, and it's wave shaping basically, it's squaring it off, which gives it kind of a different
A distorted
sound.
shape, yeah.
If you replace the LED with a speaker, and you sent something through at audio rate, it would sound like a more square wave than the triangle that you're sending through, for instance.
Well, yeah, we're going to get to that.
Okay, sweet.
Yeah, yeah. We're going to get into saturation and distortion and amplifiers and all that stuff. Cool. And I have a question here. What's Transistor Man doing here? I kind of just explained it. I was hoping to talk a little bit about the negative feedback in here, but I'm not going to do that because we're probably running low on time. Okay, so now I put this equation here in yellow to remind myself about this. What if we got rid of the LED? Because here we've got this emitter voltage is following the base voltage. Okay, what if we get rid of the LED and just have this? What we have now is a circuit where V out is equal to V in minus 0.6 volts. Now that might seem kind of useless. I mean, a wire can do better than that, right? You're not getting that minus 0.6 volts with a wire. I guess if you want to subtract, like make a calculator that subtracts 0.6 from something, you can do it with this. But there's something really cool about this circuit. This is called an emitter follower. Okay, and what it does is it outputs a voltage here that's the same except for that 0.6 as the voltage that's in. And again, this might seem kind of useless, but where is the power for V out coming from? It's coming from the battery. It's not coming from here, right? So if this is something that draws a lot of current, like a speaker or a light or something like that, and you can't provide that much current from whatever's controlling this, the transistor is giving that boost in current. Or you can think of it as a decrease in the impedance. It makes this thing here, which might be like an 8-ohm speaker, the current that you need to put into the transistor in order to put current into the speaker over here, it's going to be beta times this resistance. So this speaker here is 8 ohms. If I build this circuit with a transistor of a beta that's 100, it's going to look like 800 ohms over here. Yes?
But if you were to put an 8-ohm speaker in there, you would, since that's a very low resistance, there wouldn't be much to limit the voltage through it. I mean, there is that parallel resistor equation, but I think that resistance would decrease.
You're right, and we'll talk about that too, and that's one reason why I'm using 9-volt batteries. Because 9 volt divided by 8 ohms is only 100 milliamps, and nothing here is going to get damaged by doing that. It's not the ideal thing to do, for sure. And in real audio amplifiers, and I'll talk a little teeny bit about how to do this. In real audio amplifiers, they go through capacitors to remove DC, they go through transformers, they go through push-pull circuits, which I've got one here. There's a lot of other stuff that goes on to control the amount of power and current that's going into a speaker. Yes, so you're right. This will work with with an 8-ohm speaker here. It'll work, but it's not ideal. It's not really the way you do a professional amplifier. Yeah. Anything else about the emitter follower? Let's see it in action. Okay, so yeah, I talked about all of this. Here is my emitter follower. It's kind of a boring demo. There's no lights or anything. You don't need the ammeter anymore. Let's see. There's the input, and then output. Right. The output is on the emitter. Ew. Let's use a sine wave instead. Offset 0, 2 volts. It's too slow. Okay. Those are on the same scale, yeah. All right, so the yellow trace is the input, and it's a 3.2 volt sine wave, and blue trace is the output, and it is not a sine wave. Yeah, whether I wanted it or not, but it has to be that way, okay? And that's because, and you'll also notice, yeah, that it's down a little bit, right? The output doesn't go as high in voltage because of this minus 0.6 thing. And the reason you don't get the negative part is because when this voltage here goes negative, this is turned off. And so the collector is just open. And so it won't, this particular circuit cannot go negative. It can only follow a positive going voltage. Okay, and I can see what it looks like if I add a little offset into the input, shift it up. Let's turn the scales here down. Oops. So now what I'm doing is adding voltage to the sine wave. So instead of going positive and negative, it's going to get to a point where it's centered around like 3 volts and it goes up to 6 and goes down to 0. And you can see what happens is the follower is following it. And now see this flat thing here, that's kind of like what you were talking about, it's clipping. You're trying to push the transistor outside of where it can operate as a linear amplifier. And I can drive it too high also. I'll get to a point where it's happy. There. So now I have the input equal to the output. Okay, except for that 0.6 thing. And I'm going to turn these down again. And keep going higher and higher. Move the trigger up. So I'm just adding a DC offset to that. And I think you'll see it clip at some point here. What I'm doing with the oscilloscope is changing the scale on the vertical because I'm getting up into like we're at 7.89 volts now, and it's not fitting on the screen anymore. But you can start to see now in the blue trace. Can everybody see there's some clipping there? It's starting to get flat, and eventually, when I get up to around 9 or 10 volts, the transistor doesn't turn on anymore because I violated the rule. I've got now the base going higher than the collector. And I don't want to do that actually because of that diode short circuit, and there's really nothing stopping current, a lot of current flowing that way, so I don't want to do that for too long. Okay, but that's the other end of clipping, is overdriving it. You can drive it negative and you can drive it too far positive. And either way, it stops working like a nice amplifier. What I was doing was turning it. Okay, so that's emitter follower. Questions about that? The point of this thing, like I said, again, to emphasize, is it lets you drive something that might have a very low resistance using something that can't provide a lot of current. All right, now we'll talk about an amplifier. This is a big step forward in complexity, even though this is a very, very, very simple one transistor amplifier. There's a lot going on that I won't be able to analyze in full detail. We're going to have to look at something called biasing, which is changing, sort of like what we were doing here, moving the voltage of the base up to a point where we can apply a little oscillation to it and get that full range of nice sinusoidal behavior instead of clipping half the input off. AC coupling, I mentioned earlier about capacitors and how I'm not going to talk about inductors, but we'll see capacitors a little bit. What a capacitor does is it will remove if there is a DC offset in the signal, it'll take that out and just present it on the other side of itself with an average of what was coming in. It's more than that, essentially. Negative feedback we'll talk about. We already learned a little bit about input and output things. Now we're not going to do this. This thing is from a very nice website that had a lot of cool stuff on it, talking about, somebody asked a question, why can't you make a Class A amplifier, which is a certain configuration with just one transistor? And the best answer to it was long, and it ended up with this. This was a step-by-step construction of, you can't do it this way because of that, but you can fix that problem if you add this, but then you have another problem which you can fix by adding this, and before you know it, you're here. And what he described this as an educational level Class A amplifier, not professional. And we're not going to do anything that even remotely close to the complexity of that. What we're going to do is this, and I'll try to briefly walk you through how this is working. Where should we start? Here. Okay, let's start here. This little pair of resistors is providing a voltage, a DC voltage on the base. Okay, it's going to set it up to a certain working point, like around 1 volt. This capacitor is going to be blocking any DC that's coming in from here and changing it into an AC signal there. So there's a DC signal provided by the resistors, and then the input will provide a little oscillation on top of that. These two resistors here, it's complicated, the math, I'm not going to even show a slide of it, but they determine the gain, the voltage gain, which is the ratio of out to in. With this setup, it's around 10. And I think mine's got the same thing, and it's around 8.9 or something, probably because of tolerances and the resistors. And the other thing that I did is I changed this a little bit to help it work with another demo.
Is the gain?
Yeah.
Is the gain the ratio of those two resistors that are right there? Since the gain is 10 and 10 kilo ohms is 10 times 1 kilo ohm.
Those two resistors, their ratio, that's what determines the gain. If it was 20 to 1, then the gain would be 20. And they also determine the output impedance, which I'll talk about in a minute.
So on an amplifier where you are adjusting the gain, are you just adjusting the value of that specific resistor in the circuit?
In this amplifier, that would be so. In a professional real amplifier, they're even way more complex than that thing there. And I don't know, there's a lot of different ways of doing it. You can adjust gain in a lot of different ways. But somewhere you're turning a resistor that's changing something in the circuit, yeah. So here, if I wanted to do that, I'd replace probably the top resistor with a variable resistor so that the resistance and the gain are linear. If I change the bottom resistor, now you're dividing. So half gets you 2, but a third gets you 3, and it's not linear anymore. Okay, where are we? This is what we talked about. This is the amplifier. Okay, let me try to get this thing working. I've had pretty good luck so far getting things working. So where is it? It's right there. It's this. Now, here is our signal input, and where does it go? It goes on, oh yeah, that thing. There. That's too much voltage. Okay. These are those two capacitors on the input to remove from here. The DC signals on the input, this removes DC from the output. This thing I had to add because this signal generator makes a lot of high frequency digital noise. It's a capacitor to ground. And what that does is it takes out some of the high frequency noise and just acts like a 0 ohm resistor to ground to get rid of some of that stuff, but still keeps the audio level stuff in there. And this, because this capacitor will sort of build up a voltage on it, and then every time you hook and unhook the scope probe, the trace is going shoo, 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 shoo. It's really annoying. So I put the resistor there to get rid of that. So help get rid of it. All right, so now let's see. Here's our input. Let's make sure we've got scope on that, right? Looks good. And then the output is going to be blue guy. That goes on.
Until we can find something for you guys to pick apart.
Right. Or that resistor. Okay, so right now, they're both on 5 volts per mark. So they're the same scale. And I know this amplifier is going to multiply by about 10. So I'm going to start with 0.1 volts with input. Now the yellow one is the input and the blue one is the output. Can you see the difference between them already? What I'm going to do next is I'm going to change the scale so that the yellow guy is on a 10 times bigger scale than the blue one, which is the output. Now we've already got a little bit of a problem because there's some DC offset on there, on the output. Why is that? because I told it to do that. That's why. There. Now that sugar's pretty much gone. And that's one. There. So now the input is half a volt per division. The output is 5 volts per division. Right now the signal's applied is 0.1 volts. Now it's 0.2, 0.3, 0.4, 0.5. And you can see they're getting bigger with each other. The blue one is not getting big as fast. Oh. Yeah. See, it's clipping too, isn't it? See on the bottom there? Yeah. Hmm? Yes, that's right. I forgot about that. This amplifier, the other thing about this amplifier is that when the voltage here goes up, more current flows through here, right? So Transistor Man makes more current flow through here, which means that there's a bigger drop across the resistor. When you push more current through a resistor, there's 9 volts here. The more current you pull through the resistor, the less voltage there is on the other side. It's kind of like if you've got a hole and you're trying to push water through it, you might have 100 psi on one side. On the other side of that hole, there's less pressure, right? The resistor's doing the same thing. So a higher voltage here is making a lower voltage there. So this inverts, for one thing, and it clips. It can't go negative because we still only got one transistor with a the collector. It can't go negative. The
What
collector
if you
just
put
can't
the
do that.
capacitor on the emitter?
Well, then you start getting into some issues like we had with that diode. Now you're going to be, the capacitor is going to be doing something over here. It's going to be trying to keep the voltage across it the same. And as you try changing your base voltage, the capacitor is going to be pushing on the emitter and trying to fight with you about that. So that's not what you want to do. Why this is happening, I believe, because this capacitor C2 ought to be holding an AC coupled output. I must have something. Oh, it's still clipping. It's just AC coupling the clipped output. Right. Yeah. So yeah, that can't go negative. But again, if I'm overdriving, that's the. Let's go back to channel 2. Yeah, even though it's AC coupled, that doesn't change the fact that you can still overdrive it. And that's what I've done. It's too much voltage there. There. So now we've got a nice sum. This is still keeping it within its linear range. All right. Okay. So there's that. Gain is about 10. Oh yeah. This is kind of cool. So far we've only looked at signals that are like 1 hertz, 10 hertz. This right now is 11 hertz. How fast can this thing go? There's 100 hertz. There's 1,000. Wow.
Says I'm at 1 kilohertz.
Okay. There's 2.
Your microphone's sticking out of
Yeah. Oh, yeah, that must be it. Because I'm like, this isn't. Whoa. Magic. All right, well, the microphone's going to stop being able to deal with this in a second. That's 10 kilohertz, and something's not triggering right here. So that's 10 kilohertz, and I'm going to get ready for going further. 20, 30, 40, 50, 60, 70, 80, 90, 100.
Wow.
And it's still kind of hanging in there. It's not doing super great, especially with the trigger. So this thing can easily go up to 10 or 20 kilohertz, and which is, for audio, that's all the bandwidth you need. And actually, it'll keep going up to about a couple of megahertz, but it starts to drop the gain off because of all these capacitors that I've got in there. If I took all of that out, I drove this thing up to about 5 megahertz. The transistors are capable of switching at around 20 or 50 megahertz, so they're plenty fast. Okay, any questions about our... Oh yeah. We already showed it can drive a wireless microphone, but can we hook a speaker up to this thing? Here we are at 1 kilohertz. Can we hook a speaker up to this and get any sound out of it? Well, let's see. Now this thing I was totally not prepared for. Ground right there. Output is right here. Why? The trace went to 0. Well, we're on such a high speed you can't see. So there it is, nice and happy, about 1 kilohertz. It's got a little clipping, but it's doing something. And I hook the speaker up and it's 0. That's because this is an 8 ohm speaker. There's a lot of voltage. This is, you know, it's like 5-6 volts, something like that. There was 20 volts coming out of my finger. But the output impedance of this amplifier is 10K because this. See here, the power for this thing is coming from here. That's going through that. So the output impedance of this amplifier is 10,000 ohms. We could lower this and lower that, but what starts happening then is this is acting like a short between plus volt and ground, and you start dissipating a lot of power. So, you know, you can play some games with that and maybe find a spot where you're happy with it, but it's going to be really, really difficult to drive that 8 ohm load from this kind of an amplifier. And that's why they use transistors. We've got something that can do this. We just looked at it. Yes.
Another transistor? Another transistor?
Yeah, well, how about that emitter follower that we were just using? Right? If I said it lets a small load look like a big load. A low impedance, like the speaker, look like a large impedance. So it's going to multiply this 800 by its beta, which I think is around 150 or 200. So it's now going to look like about 1,000 ohms or something along those lines, if I can hook this up right. So what I want to do is take the output of the amplifier, which is right here, hook it to the input of the follower, which is right there, and then put the speaker back online, the ground here, and the output of the follower is at the emitter. Now that's pretty quiet, but it's real. Hear it?
Yeah.
I could have swore I had better than that going. Well, it's louder in my room, in my apartment. It's pretty quiet here, but you can hear it. And it's definitely there. It's not the best setup. I haven't got all the biasing set up right to keep everything in the linear range here. There's some clipping on it. It's taken a huge amount of current out of the follower transistor. I really should have multiple stages for this, but it is doing something, and it's getting the basic point across, right? That you've got an amplifier with a lot of gain, but it's got a high output impedance. There's a follower which can produce more current. You can hook them up and get something that's a little bit more useful. Very little bit. All right. So that's good. What if we want positive and negative outputs? This has come up a couple of times so far, and nothing that we've done has done that. Everything that we've done so far has been positive outputs only. And that's not good for the speaker either, because it's keeping a DC current flowing through it. So it's burning power, It can affect the magnetism of the speaker, other things like that. You don't want to put sustained periods of direct current through a speaker. So how can we get something that's going to go up and down, positive and negative? We tried using a capacitor to remove DC, but there's something else that we can do. And that's called a push-pull amplifier. And this is how they work. They use an NPN transistor and a PNP transistor. This is pretty straightforward. I mean, there's hardly any resistors at all, and the only reason that one's there is to stop the transistors from getting too hot. But you put a voltage in here, that voltage turns on this transistor, current flows, goes through here. If the voltage goes negative, that turns on this guy, right? Because this emitter base turns on when this voltage is negative, when the base is lower than this emitter. And so then collector says, I need current flowing out of me, and the only way you can get it is to pull it through the emitter, so that now gets current going the other way. Is that making sense? Okay. And that's called a push-pull driver for obvious reasons. One side's pushing, the other side's pulling, and it's a driver, not an amplifier. This doesn't give any voltage gain. Okay, it only gives power gain. So you're controlling on the speaker side of this thing a larger current than what you're putting in on the base side. And I have one of those here, and it works even better. In this setup, okay, so the push-pull guy is this. And I put that 12 ohms there so that if the voltage goes up too high, there's not too much current flowing through the transistor. And I hope. Oh, I sure didn't. Okay, so now I'm going to have to try to figure out on the fly where the input and output are on this breadboard. The input is the bases, the output is where that 12 ohms is. Yes. 12 ohms is right there. And then the input is on the bases, which is this green wire that you see. And of course it's not either. Oh, you know why it's not working? Because a push-pull amplifier, look real close here, it's that. I've only got that. Okay. Now, I need to be very careful not to hook this up backwards. I want the red side to be -9. So this goes to this goes to the plus. That's working a lot better. But it has a little bit of a problem. Is channel 2 hooked up to this? So what do we notice about the input and output here? The yellow is the input and the blue is the output. Yeah. It's kind of annoying, isn't it? Let me keep it here just for a minute. So the yellow is a nice smooth wave, right? And then the blue one, you see what's going on right here?
Is that like both of the transistors having a small clipping period?
Yeah, there's a period where neither one of them is turned on. And I've got a simulation of this, so I'm going to turn this thing. I'm sure it's driving everybody nuts. Okay, so I mentioned it's not an amplifier, it's a driver. It outputs both positive and negative voltages. Most of the current that's flowing is going through the speaker. And I talked about the resistor. And otherwise the transistors get hot. There, each of them was carrying about 400 milliamps. They're only rated for 200, but you know, whatever, they're cheap. Without that resistor, it's pushing an amp. And that they were starting to smoke, really, like literal smoke coming out of them. So what this is called is crossover distortion, and it's a real problem with push-pull amplifiers, which is pretty much anything, unless you've got a transformer on the output. Then you can do some other stuff. It's caused by the it's called a dead zone, where the top transistor, the voltage is too low to turn it on, and the bottom transistor, the voltage isn't low enough to turn it on, so they're both off, and the output voltage is 0. And you can hear it. If I could tune this a little bit better, you'd be able to hear the difference between a sine wave coming out of that speaker and that distorted thing coming out of the speaker. It's very quiet. This is too quiet to hear that, but believe me, it's a very noticeable difference. Even though optically there on the scope it didn't look, it's just a little tiny, but you can hear it really, really, really clearly. There's a lot of tricks to get rid of that. One of the best ones is to put a biasing network over here and add a diode in here to match this drop here, so that the base of this transistor, when the input is 0, that base is at 0.7 volts, and it's just about to turn on. And then do the same thing down here. Put another diode there, so that when this is at 0, when the input's at 0, the base is at minus 0.7, and it's just about to turn on. And then as you cross through 0, this guy's turning off, and this guy is simultaneously turning on. And I tried that, and it works. The problem with it is that unless you very precisely balance and match everything here, and even if you do, there was a period where they're both on at the same time. And that looks like a wire, through a wire, through a wire, to -9. And talk about smoke. So I didn't bring that circuit today, because it's a transistor destroyer. What you need to do is get power transistors, bolt them to a big metal thing, and dissipate the heat away. It will work. Okay, the last thing I want to talk about is this. This is a really cool thing that you can do with transistors. And if you remember at the beginning, I took an oscilloscope probe, and I touched it, and I'm doing that again here. And I got this, so let's just look at that. Okay, now that is a very ugly looking wave. It's all of the electrical noise in here that's being radiated at the power line frequency, which is 60 hertz. And it's not a pretty sine wave because all these different things are interfering with each other. Some of them are linear, some of them are not. So we can't drive a speaker with that. This setup will let us do something pretty neat. We'll be able to hear that. What this is two transistors connected together. You put a little current here, that turns this one on. All the current through this transistor is going into that guy's base. So it really turns this one on. Okay? And what this ends up looking like is one transistor with a beta that's equal to the product of these two betas. So this one, I think that transistor has a beta of 498. I measured that, and this one was 250 something. That, by the way, reminds me, that beta number varies from transistor to transistor widely. I mean, just within, they're the same transistor, I got it in the same drawer right over there at the same time. They've got the same markings on them, and there's a factor of 2 difference in beta. So you can't rely on beta as a design parameter. Okay, so this works. So this thing here that I've got is going to have it's going to act like a transistor with a beta of whatever 250 times 500 is. I can't do that in my head, but it's big. Hundreds of thousands, 75,000 or something like that. The problem with this is, or a problem with it, is that you need a higher base voltage to turn this on, right? Because you got to turn on this base emitter thing, and you got to turn on that base emitter thing. So you got to get now, instead of bringing the base up to 0.7 volts, you need to bring it up to 1.4. Okay, but what you get in return for that is this double beta thing. This is used for detecting very small currents, like we're going to do, or for making a small load look like a big load, or power output stages in some audio amplifiers use this because they're trying to drive over here, you know, maybe 10 amps, and they don't want to be having to generate 10 amps over there to do it. They use a small control signal, so this gets you a huge current gain on an output driver stage. And all we need for this is the battery, which is already hooked up, and the wire, and the speaker. So the speaker is going to go, let's see, output this. What did I do? I put the emitter to ground. So the output is the collector. Yeah, both collectors contain base. And then the input is the base, like the first one. Let's hope this does something. Nothing. Because this is plus. There we go. Like I promised you, we can hear that. So what this is doing is it's making that 8 ohm speaker look like, I don't know, whatever 500 times 250 is, times 8 ohms. So if it was 500, it would be 25,000, 250,000. So it's like 100,000, let's just say it's 100,000. So it makes that look like an 800,000 ohm resistor. Remember I said this probe is about 1 million, and you can see it on the scope. So that is what the power noise around us sounds like. And I'm glad you could hear it. That home barely worked unless I grabbed an actual power line with one hand, like an extension cord, and then touched that. Okay, so there we are, the Darlington thing with the speaker. Oh, and again, we talked about this too. This is just for fun. You don't want to hook up a speaker like this with a DC path to ground. We talked about that. Do we have time for a little bit more stuff, or we like use it 3 o'clock or something?
It's 1:45.
Oh, well, I said 90 minutes. Not a little bit. Let me, I just like 5 more slots. How do you choose a transistor? For most projects, all the things on here are these two. These are very good. They're very common. The 2N3904 is an NPN, and the 2N3906 is the PNP. If you need a slightly higher collector current, the 2N2222, I don't know why they named it that, but maybe it was just the next one in the sequence, but it works almost the same as the 3904, but it can pass 1 amp through the collector. Packages. These are all the packages I have here. Is this little package is called TO92. The pins are labeled 1, 2, 3 with the flat side facing towards you, and it's virtually universal. That this is the emitter, that's the base, and that's the collector. Almost every transistor in existence is done that way. The ones that aren't have it labeled on it. There's other packages too. These are like the big high power things that need to get bolted to a frame to dissipate heat. And there's some other stuff there. These are little surface.
Why did you leave the
And then I said,
TO220 out?
I'm sorry?
Why did you leave TO220 out?
Yeah, because I forgot about it. He's right. There's also the TO220, which is the little round can thing.
No, TO220 I thought is the stand that
Metal.
is a little bit bigger than TO146.
Ah.
It looks kind of like it, but it has a metal thing.
Oh, okay. Okay. I just forgot about that one. There is another one that's a round metal can that I don't think they make anything of those anymore today. I think that's the TO3. All right, so field effect transistor. This is cool, and probably it would have been easier if I'd done this instead. These are similar to bipolar junction transistors. They're arranged in NPN setup, but they use a different kind of magic to make the thing work. The control is by a lead. What we've been using is called the base on FETs. They're called FETs, F-E-T. It's called the gate, and the other two leads are called the source and the drain. The difference here is, remember, Transistor Man is looking at the base current. The FET equivalent of him is looking at the base voltage and changing the gate, the drain source current. Okay, let's mention that. And as a result of the way they're made, what's cool about them is the gate draws almost 0 current. It is microamps. Yes, we have a lot of interesting questions.
Does a FET have like that type of turn on voltage? Like, is it 0.7 volts or is it always?
It's different, but the same kinds of things apply to it. And I'm not going to go into FETs because, I mean, I'm already over time, way over time. So I had to choose things not to talk about it. FET was one of them, except to just show a picture of it and to explain what I just did there. So this is all I'm going to say about them. They're constructed a little differently. There's an N here and an N there and a P in the middle. And the gate, instead of doing that recombination thing that a bipolar junction transistor does, it does something different. The electric field from the gate causes this P to sort of change into an N. That's the easiest way to understand it. And this is not a semiconductor layer here. This is an oxide layer. It's basically glass, and it does not conduct electricity. It just doesn't. So they're very, very good for high impedance input things because they have they don't take any current. So that's a FET. So summary, we talked about diodes, we talked about recombination and the transistor magic, we talked about transistor man, we showed how transistors can be used as switches, and then we saw some applications, and we talked about input and output impedance. I think that is it. Yes. Okay. Any questions about anything? Thank you.